The math is actually pretty straightforward. So the x of k, which is our DFT, is equal to our x of e to the j omega, which is our DTFT, sampled at every omega equals 2 pi k over capital N, where capital N is the number of samples in our original time waveform. So that's how I think of it. But you can directly compute it by taking the formula for the DTFT and substituting this in which case you get it's the sum from n equals 0 to capital N minus 1 of x of n e to the minus j 2 pi k n all over capital N, and that's true for k varying between 0 and capital N minus 1. And you can reverse it with this formula. And unlike DTFTs and everything we did in continuous time signal processing, this inverse function is used all the time because it's just another summation. So on your note cards for the next test, you definitely want to have this. You can write your own code to compute the DFT. You can see that for every output value k, you're going to have a sum of n samples. And you're going to have to do that n times because you'll have n samples of your DFT. So if you try to compute this directly using MATLAB, you can, and you'll end up with something that has order of n squared operations. And if that's where we kept things, the field of DSP probably would never survive, would have never been developed. Instead, it's because Cooley and Tukey developed the FFT, well, I guess Gauss did first, that found a way to compute it in far fewer samples.